Okay, so right where we left off, this is how we actually define a Tesla. Alright, from this equation, we see this as a Newton over an amp meter. And remember we had the conversation that all units are based on those 7 fundamental units. So in this case, we call a Newton over an amp meter a Tesla. So we haven't had to break it down before now, but this is where it comes from. Okay, and so when we go to look at units, it's always going back to this equation that we figure out or can remember what a Tesla is. Okay, this is known as the Bill equation, right? BIL sine theta, Bill. Now, we also need, though, to get a direction. And so we have a new hand rule. And our new hand rule is called the right hand slash left hand palm rule. Okay? And so what the rule says is you point your fingers in the direction of the magnetic field. So in this picture up here, with the appropriate hand, of course. So I'm going to use my right hand because that's the one I'm not using to hold the camera. So point your fingers in the direction of the magnetic field. So they're going to go into the page. Okay? Now they can go into the page either this way or they can go into the page this way. So the first part, point your fingers in the direction of the magnetic field. Second part, point your thumb in the direction of the current. So that means my fingers have to go this way so my thumb can point over here. Okay, so my fingers in the direction of the magnetic field, my thumb in the direction of the current flow, and the force comes out of the palm of my hand. So the wire is going to experience a force going towards the top of my paper this way. The force on the wire will be, this way, except it's not really electron current because I was using my right hand. That's for conventional current. Okay? If it was for electron current, it would be downward, but it's too hard to use my left hand because I'm holding the thing with it. Okay, so again the rule is point your fingers in the direction of the magnetic field, point your thumb in the direction of the current flow, and the force will come out of the palm of your hand. It's kind of like Spider-Man or maybe Iron Man, right? So the force comes out of the palm of their hand. For Spider-Man, it's the web. For Iron Man, I think it really is this force. And so if you were to do this, if you were to put a current carrying wire in a magnetic field just like this, you would see the wire jump. Okay? It would actually move as a result of the force. Alright? So that's the right hand, left hand palm rule. Maybe the one other thing I should tell you while I still have a few minutes on this video before we do the homework, and that is magnetic field strength of the Earth. Your textbook uses 5 times 10 to the negative 5, but for us here where we are, it's really 5.5 times 10 to the negative 5 Teslas. It mentions it at some point in the chapter in the textbook, but then it asks it expects you to know it in some of the questions at the end. So 5.5 times 10 to the negative 5 Teslas is the strength of the Earth's magnetic field. This F here, if you want to be consistent with physics, this would be like FB, F of the magnetic field. We don't tend to put it on our F's in this unit because they're all going to be FBs, but that's what it would be. Okay? I'm wondering if I should do a couple more examples of hand rules. Maybe I will, just before I tell you your homework and then before we do homework. So let's do, here's a magnet with the north, here's a magnet with the south, here's my wire. This time I will do electron current just to keep you happy. Okay, what is the direction of the force on this wire? So try it for a second. So you point your fingers in the direction of the magnetic field, And this is where you need to know that magnetic fields always go which way to which way? I hope you're saying north to south. So the field lines are going this way. So with your left hand, your fingers would be going that way. And your thumb would be pointing towards the top of the page. And this wire then would experience a force out of the page. Okay? If we do another one, let's put our south here. Let's put our north here. Let's put our wire like this. We'll put a little dot here. And so the question is, what is the direction of the force if the current is flowing as indicated by the dot and the current is conventional this time, just to keep it exciting. Okay, so take a second, see if you can do it. Again, you need to know the direction of the magnetic field, always flowing from north to south. So the magnetic field lines are going this way. It's conventional current, so it's your right hand. You need to know that the dot means coming out of the page. So your hand will go like this, fingers toward in the direction of the magnetic field, thumb upward. Force will come out of the palm of your hand, which will be going this way. Okay? So that's that one. We didn't do that many examples for the other hand rule, the curl rule. So let me just draw one here that should totally complicate your life. So we'll do this, and just for fun, I'll turn this around. And then I'll do this. And the question would be, are these electromagnets, are they going to attract or repel? Okay, are they going to attract or repel? So what you'd have to do first is figure out which is the north and which is the south for each of them. So choose if you want to do electron current or conventional current. I have my positive terminal over here this time, so if I do electron, it'll be coming down on this side, down, down, and going up. And so then with the electron current, curl your fingers in the direction of the magnetic field, and your thumb will point in the direction, curl your fingers in the direction of the current flow, and your thumb will point in the direction of the magnetic field. So you should get the north over here on this side for this one. Okay, and if we do electron current over here, down, up, 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 and again with your left hand, curl your fingers in the direction of the current flow, and your thumb will point in the direction of the magnetic field. That'll make this side north. So if this is north, this is south, and this is south, these two are south are facing, they'll repel. Okay, so I'd like you to try a few questions for me, and then I'll do one more video with your questions from last night. But for tonight, or for today, for homework, you could try on page 504. I think these were the ones that Peter wanted to do over the weekend. Page 504, numbers 9 to 12. And these are with F equals BIL sine theta. And on page 511, and that's 511, 512. These are the problems now. I'd like you to do numbers 3 to 12. I think I actually had assigned 3 and 4 before, and I forgot to go over them yesterday. Okay, so these are all with F equals BIL sine theta. I know it might seem like a lot, but I think they're pretty simple. And we also didn't go over the multiple choice questions yesterday from the multiple choice page. So I'm going to add a few more to those because these are more hand rule-y ones. So numbers 6 to 8 and numbers 11 to 15. Again, I know that seems like a number of questions, but they're all each going to take you about a minute. So they really won't be too bad, okay? And we'll go over them tomorrow in class. and review the hand rules. And it might be time for a hand rule quiz. You now have 3 hand rules. You have